Okay, sorry, Marley. You missed one of the practice problems. So I'm going to go ahead and post these notes along with the recording so that you can look through them. So we did this problem first. So it's a Q versus K. And then we're just getting started, like making sure we're clear on what we did last week. And then we're doing this one that's quite a bit more complicated. We're going to have to actually solve through the ICE table and determine what BRCL concentration is. So a couple things I mentioned is we're going to go ahead and just assume that the minus X doesn't matter and then see if it does. Now, I don't really want to go through and do the quadratic formula and do all the foiling. So we're just not going to. In reality though, and this maybe come across like in lab or something, you can tell that you're going to have to because the value is big enough that if I take 0.993 and subtract 0.00498, I get 0.998. No, 988, sorry, for this amount. So like that is different than 0.993, significantly different. So that's going to affect, like this value here should be 0.988, and this one's going to be different as well. So it is going to make your number off if you make that assumption on this one. We've said the standard is if the K is times 10 to the negative fifth or smaller, you can ignore those minus X's and plus X's. And in this case, it definitely didn't work, and we kind of proved that that's too big. I'm not going to go through and do it. If we had time, energy, I would. You can do this on your own at home if you want. You could go through and take this. You need to multiply the denominator terms, like FOIL them out, and then set everything equals a 0, and then put it in a quadratic formula solver, or actually solve the quadratic formula. Okay? So I'm not going to give you one like this on the test. I think there's one on the Pearson, like maybe one on the practice exam and one in the homework. So be aware of that.
Can I show you this?
Yeah.
This is what how my calculator's doing.
Yeah.
So my phone gave me the right answer,
Okay.
but that gives me that. So it's like
Yeah. So 10 to the negative 1 means you move the decimal
move
that
the
way.
decimal. Okay.
Yeah. Do you want me to just take it out
Yeah,
of
I was
scientific
gonna say, I
mode?
just hate that it's in that. Just
Yeah.
always supposed to
So mode probably. No.
Because it will first give it to me in the fraction, but you get that like S to D to get
Yeah.
out of it, but I just don't know how to get it out of that scientific notation.
Mm-hmm.
I've asked so many people and they're like, I don't know. I read them
Tell you what, let me look at it. I thought it was going to be easy. Let me look at it a little bit more while you guys do another problem, or when you do another problem. So just use that for now. Okay, so let's talk about the last topic in this section. So yeah, we stopped here the other week. So the last topic is Le Chatelier's principle, which is this idea that if you have a system at equilibrium and then you change something, we often say you apply a stress, the reaction will shift either to products or reactants to relieve that stress. So it's going to go whichever way it needs to relieve that stress, or what we really mean is to get it back into equilibrium. What the heck? There we go. I can cannot sit all day. My back is bugging me, and sitting is 10 times worse. Okay, so we're going to use this as our example. Let's pretend we have this reaction, and let's pretend it's already at equilibrium. Okay, that's a key point, is that Le Chatelier's only applies once you're actually at equilibrium. Okay, and we want to predict how these stresses are going to change the system. So there's kind of three main types of stresses that we're going to talk about. So I'll summarize that up here. So the first is changing concentrations or amounts of any of the stuff. Changes in pressure, which is related to volume, because from the gas laws, you guys know pressure and volume are inverse. So if you decrease the volume, that increases the pressure. And then the last thing is changes in temperature. So adding or removing heat. Okay. So maybe let's look at this picture first and then do the sample problem. So they're saying we have equilibrium at this point for this reaction, N2O4 goes to 2NO2. And if you add more NO2, you have now offset that balance point, the equilibrium point. And so it has to do something to re-achieve equilibrium. So like, let's pretend the balance point was like, oh, we can actually see, because it's, it looks like it's slightly product heavy, because you've got 1, 2, 3, 4 of those. Oh no, it's actually exactly balanced. And then 2 of these, and the mole ratio is 1 to 2. So it's exactly balanced between reactants and products in their picture. So if we add more NO2, we've got to convert some of that to N2O4. So it's like we messed it up by putting in too much product, and we got to get it back to this point, to that equilibrium point. Okay? So the way we do that is just shift it backwards, make more of the reactants so that they level back out again. Okay? So whatever you do that stresses it out, like we have too much product because we add the NO2, it needs to re-achieve equilibrium by shifting one way or the other in order to hit that balance point again. Okay, in this example, it's going to shift to the reactants. Some of that NO2 is going to react and form N2O4 so that we hit that balance point again where they're approximately equal. So they're not showing you the end picture here. They're showing you that these guys are going to react. So like this will be a new N2O4 molecule. So now you've got 1, 2, 3, 1, 2, 3, 4, 5. So it's not perfect, but it's as close as we can get. Because if we make another N2O4, then we're just going to be offset on the other side. Okay, so let's look at this example and see what happens when we add A, B, and C or remove A, B, and C. Okay, so adding any of the reactants, so the first two, if I add A or if I add B, it's going to have to shift to get rid of some of that. So when I say relieve the stress, that's what I mean, is shift the reaction to get rid of some of that stuff we just added in. So for both increasing A and B, it's going to shift the reaction to the products, meaning A and B will react and form some of C. So here's our original balance point. We mess it up by adding some reactants. So we need to shift the reaction. That'll decrease the reactants a little bit and increase the products a little bit where we have that same balance point. Don't forget the values, the actual amounts aren't going to be the same, just like in this picture. You don't have the exact same number of molecules. It's the ratio that you're trying to achieve. So like, it's not going to be, oh, I had 5 of these and 6 of these, and now it's 5 and 6 again, you might have it be 10 and 12 or something, so that it's the same ratio, it's just not the exact same amounts, like 2 to 4 versus, 1 to 2. Same ratio. Okay, so similarly, if we do the opposite where we increase C, it's going to shift the reaction the other way to get rid of some of the C and make some of the A and B. So you apply a stress, it goes whatever direction it needs to get rid of that stress. You've got too much C, it goes to make reactants to get rid of some of that C. Okay, take a minute and predict the decreases now. So if we decrease A and B, how would the reaction shift to compensate? Or if we decrease C, how would the reaction shift?
Wouldn't it just flip-flop?
Yep. So if I decrease A and B, it needs to make A and B to compensate. So it's going to go that way to make some of that stuff. If I get rid of some C, it's got to go that way to make some C to replace it to re-achieve that equilibrium. Okay, so that's changes in concentration. All right, let's focus in mostly on these two here, but I'll let you guys predict the others when we get to it. Okay, so new reaction, 2x plus y goes to z. A little bit of a trick here. That's a solid, and remember, solids and liquids, we don't incorporate them into the equilibrium constant. Don't worry too much why, because the answer we give is actually a lie, so, unless you're a chemistry major, you wouldn't actually get a real answer. So just don't include those in the equilibrium constant. So similarly, they won't be involved in any of these shifts. So if you increase the amount of X, the reaction's not going to move in any direction. Okay? So changing the amount of a solid and liquid, unless you drop it below a certain threshold, it's not going to affect how the reaction proceeds. So no shift. Soft. Okay, so for these volume ones, what they're actually really asking you about is pressure. So if I increase volume, pressure will decrease. If I decrease volume, pressure will increase. So pressure we define as like how often the molecules are hitting the sides of the container. That's how I always describe it. So if we make the volume smaller, the molecules hit the sides of the container more and exhibit, measure a higher pressure. Assuming you keep everything else the same. Okay, so when we say half the volume, decrease the volume, we're saying an increase in pressure. If we double the volume, we're saying a decrease in pressure. So the way that pressure affects things is that the stress you're applying is there's a pressure on the system, so you need to go to decrease that pressure in the first instance. So if I increase the pressure, somehow I need to proceed the reaction so that the pressure drops. The other thing that affects pressure is how many moles of gas you have. This is all coming from the ideal gas law. Okay, so these guys are staying constant. Let's just focus in on pressure and number of moles. So if we want to drop the pressure, we need to drop the number of moles. We can't do that by just removing stuff. So what we do is we shift the reaction, or the reaction shifts on its own to go to whichever side has the least number of moles of gas. So in the first example, decreasing the volume increases the pressure. How do we decrease that pressure? The reaction will drive to the products because there's only 1 mole of gas here and 4 moles of gas there. So as you shift to make more product, you decrease the pressure back down simply because you had, 4 moles of gas hitting the sides of the container, and now for every time you push the reaction that direction, you've dropped it from 4 moles down to 1. So it's a little bit weird because we're used to thinking of the equilibrium constant as just involving amounts, but it turns out that it actually responds to pressure, it responds to temperature. And so we see that when we put these stresses on it. So if we increase the pressure, it would go this way to the fewer moles of gas. So anytime you look at these, you want to only look at the moles of gas because those are the only ones that are going to exhibit pressure, and then decide which direction they shift. If they were the same, it can't choose. So it's just going to stay where it is and deal with the stress. Okay, now if the pressure goes down, it wants to replace some of that pressure. It's going to go to reactants to make more of Y, because you'll make 4 moles of it. There's more moles of it. That'll bring the pressure back up. So this is this idea. You apply a pressure, it's going to go to relieve that pressure, to kind of like do the opposite. It's okay so far? We're good? Yeah? Okay. All right. This one has a little picture. It's describing the exact same thing we did. I could have used that earlier. Okay. All right, so last thing is temperature. So this is actually interesting because depending on how much you guys talked about heat in first semester, I'm going to assume none, because I actually think that, I'm pretty sure you probably didn't have any discussion about heat. So this is like the change in energy. I think we said earlier in our class, if this value is negative, then we define that as exothermic. You don't have to remember the name, but it basically just means that heat is released as part of the reaction if it's negative, if that value is negative. So when we say that you have a negative delta H, or heat being released, you can actually think of the heat as a product, because when X and Y come together, they make Z, but they also make heat. It's not mass, but it's some energy being made. So I'm actually going to write plus heat as a product, like pretend like it's a product. So now we can treat it just like we did the concentration stuff. So if we increase the temperature or add heat, which direction will it drive? So if we increase this, it's got to go to the reactants to get rid of some of that heat. Now that's actually true. Like if you take Z and combine it with heat, you can make X and Y again. It's going to shift towards the reactants. Similarly, if we drop the heat, it's going to need to make some, so it's going to shift towards the products. Okay, so last thing that's like new stuff in the chapter, or I guess it's just a practice problem, but let's go ahead and have you guys take a look at this for a minute and try to predict the direction that the reaction will shift for each of these. And then I think we'll move on to, maybe we'll do one more practice problem with the ice tables before we move on to 17. So the idea was we're doing finishing 16 today, so 16's homework will be due this weekend, and then 17 prep was already done, so you're done with prep assignments. Did I update those? Did they look normal? Like just the videos and the associated questions?
Mhm.
Okay.
I just looked at mine today though, and for some reason I have a 0 for my chapter 15.
Dynamic study modules.
Yeah.
There's this weird thing where it's not letting me put late points in. So I have to like manually go in if they're turned in late and update them.
Okay.
So I'll
I
do
don't
it at the
even
end of the
remember-
semester, but I'll try to remember to do it before then too.
Okay. I just don't even remember turning it in late. Like I have been calculating like what
Yeah.
my grade would be, and
Okay.
I had always had it done. That's why
Yeah.
I'm confused as to why it says it was late.
I wonder if I messed the date up too, so I'll check.
I just have late
So
ones,
for
that's
this
okay.
week, just this weekend, do 16, and then next weekend will be kind of heavy. So I would start the chapter 17 homework, because we're gonna do some of it today. And then the next weekend will be finishing the chapter 17, practice exam for 16 and 17, and then the last exam on the last day.
We have
It's
two
getting
more
close.
Classes left.
2 more classes, finishing 17, and then the final day with an exam. Okay, I'm gonna stop talking for a second, and I'm also gonna look at your calculator and see if I can figure it out. I feel like I can see on here where it should be. 'Cause there's this thing in the setup that says, oh. I think I got it. Hold on.
Yay.
Now, if it is a ridiculously big number, is it going to put it in scientific notation? Because you do want that. So when it does that, what do you press?
You just hit this SD for whatever.
Okay,
reason.
so that's kind of nice because it gives it to you in scientific notation when you do it. But like, if I just put in that, now it gives you as a
Yay,
real number.
okay. Thank you.
Yep.
Because I literally specifically bought this for exams because I'm just used to using my phone and having
Mhm.
an exam calculator for my
Yeah.
exams.
Yep.
And then when I get it, I was
You're like,
in the
I
middle of an
don't
exam and I was
know.
like, oh great, because this is not giving me the right.
I know. I always try to tell people like use whatever calculator you're using on the test when you're doing your homework because then you get used to it. But then never, it's never around or whatever. Okay, so in this one, the delta H is positive, which means that heat can actually be thought of as a reactant, something that's needed for X and Y to become Z. So this says which will cause a decrease in the concentration of Z. Let's just go through and say which direction will it shift, and then we can talk about which one causes a decrease. Okay? So increasing the size of the container is going to drop the pressure. So we need to shift the reaction to more moles of gas, which is the reactant. So there's 3 moles of gas, 1, 2, 3, on the products or reactant side and just 1 mole on the product side. So it's going to shift to reactants to bring that pressure back up. Increasing the concentration of X, we'll need to get rid of some of that X, so it'll shift to products. Increasing the temperature is like adding heat, which is a reactant. So again, it's going to shift to products. And then we didn't talk about catalysts. They just speed up reactions. They don't change anything, so that won't shift at all. But I won't ask you about that because we haven't done catalysts, but in case it comes up in the homework. So only the first one is going to decrease the amount of Z because it'll use that up and go to form reactants.
But isn't it for increasing the concentration of X, wouldn't you have to pull from Z in order to make an equilibrium?
So if you have too much of this, so it's like, here's your balance point, you added some X, and now you need to get back to where they're equal, let's just say, then you need X to come down and Z to come up. And the only way to make that happen is for X and Y to react and form Z. So you get a little bit less X, a little bit less Y too, and then Z being made so that they're back to that balance point. Because you can't like change one without changing the others. So that's why it's just which direction does it proceed. Okay, let's do one more practice with equilibrium and then we'll take a break. So let me decide which one of these I want to do. Ooh, this one looks good. Where is the K value though? Oh, yeah, let's do this. So it's giving you the equilibrium concentrations. So that means you can find what K is equal to. And then you're going to shift the reaction by adding some chlorine. So the new initial Cl2 is going to be 0.1 plus 0.4 or 0.5 atmospheres. So these guys aren't changing. Those will be your new initial amounts in your ice table. But you're adding chlorine. Now from the Le Chatelier stuff, if the reaction was at equilibrium and then we added chlorine, we know it's going to shift that way. You could solve the Q and figure that out, but we know that it's going to shift towards products. So go ahead, start by calculating the K, and then go through your normal steps of an ice table. Anyone else get 20 for your K?
That's what I got.
Okay. I'll kind of leave it there for a minute and let you guys catch that up.
So then the change will always be minus x, then 2x.
No, because it incorporates the coefficients here. So since these are 1, this is just minus x plus x.
Okay.
Yeah. So on this previous one, it was plus 2x because this had a
Because of the
2
two, okay.
coefficient. Yep. I actually think I might play around with teaching regular old stoichiometry like an ice table, but not equilibrium. Don't incorporate that idea. Just say like final values or something, because I don't know. I gotta play with it, but it's just an interesting idea to teach it in first semester like that, because it might make limiting reactants make more sense, right? Like in this case, if they're both 1 mole, you know that the minus x is going to be 0.3, even though you have 0.5 of the Cl2, because you only have 0.3 of the CO. I don't know, it could make it harder. Just an idea.
So then we just plug that into K
Mm-hmm.
after you're done.
Yep. So there's really no way of getting around these minus x and plus x here, because your value is 20. It's just huge. So we're gonna have to solve this out. So feel free if you want to step along with me to do the foiling. more stepwise. I know, it's annoying algebra. I did that one. Morgan, are you spacing out?
No, I just haven't seen someone foil in so many years that I'm like watching you do.
Oh, okay. So I did like a weird order here, but I did that
I
one.
was gonna say it's kind of backwards.
And then I did this one. I don't know what I was thinking. It doesn't matter. You just have to get all the terms in, right?
Mm-hmm.
And then I did this one and that one. So then I'm going to multiply them all through by 20. So 3 minus 10x. Let's see.
It's also making me think about how I have to take calculus in the fall, and I don't even know how to foil, so I'm kind of scared.
I know. It is that, yeah.
It's scary.
Yes. Okay, so 20x squared, and then we still have 0.6 plus x on that side. So now I need to move that stuff over and combine like terms. So 0 equals, I'm going to subtract the 0.6, so 2.4 here, and then combine minus 10, minus 6, and minus 1 from the other side. So minus 17x plus 20x squared. Let me rewrite that in the right direction for doing. Okay. First of all, did anybody else get to this point? And if you did you get the same thing as me?
I'll just take your
So
word
then-
for it.
I'm sure you will.
It's x squared? No.
Yep.
Okay, that's fine.
And it's positive because negative times negative. I'm just gonna double check myself here.
So would it be easier just, because I don't know what you did, I know where I'm at. Would you just multiply that whole denominator to the other side?
That's what I did, yeah. I mean, you could foil it first.
That's what I did. I ended
That's
up folding it
fine.
first, and then you just multiply that by all by 20.
Yeah.
Okay.
I'm just making sure that I did everything right so I don't end up giving you guys the wrong stuff. Minus 0.3 minus 0.5 plus x squared, okay, times 20. 3 for that. 10 for that. 6 for that, and negatives 20x squared. 2.4, because it's minus 10, 16, 17. Yep, that looks good. Okay, so let me just show you what I would do then to, I forgot how that happens. Okay. I'm going to pull it up and then switch it back over to this. Oh, not guest. Secure.
And then that's supposed to be set equal to 0, and then that's when we plug it into something?
Yes, and I'm going to show you what it looks like. I just put it in first and then I'll turn it back on. It doesn't let me do my internet and show you at the same time because I'm using a Wi-Fi. 17. Negative 0.6. No, that's not right. What was it? 2.4. Ah. That can't be right because it's coming out as 0.9. 20, 17, and 2.4. Did anyone else get to this?
You got 17?
Negative 17x.
I got negative 15x. Oh,
Uh,
no, you're right.
Because you subtract the
Yeah, you
x
subtract
on
the
that
x,
side.
right.
But it can't be right because it's coming out to be 0.97. Let me go ahead and show you. Oh, I need to switch this first. Great, I'll spend our break time figuring out why it's not working. Okay, so this is what it'll basically look like. So again, you have to have it set up to 0, and then you put in what A, B, and C are. A being the coefficient to x squared, B coefficient to x, and then C, the one that's just a number. So I put that in 20. Oh, do you see that? It was not negative 20. That's where it is. Phew. Okay. Was it supposed to be? Yeah, so I forgot the negative on the 20, so I'll do that in a second. So when you get the value, the reason I knew it didn't make any sense was because the two values are down here. Obviously, it can't be negative. 0.97 though, that can't be right because I have to subtract it off of 0.3 and 0.5. So that would give me a negative equilibrium concentration. So that's how I knew off the bat that I had a mistake. Again, the only time you're going to have to do this is in a homework setting, or in class, not on an exam, because it's just like, that's just too much. That's math class. That's not chemistry class. Okay? So I'll put that negative 20 in a second. Wait, it's positive here.
Mine's also positive.
Ah. Okay, I will figure out where the error is because it'll drive me nuts if I don't. All right, let's take a break. 10 to 15 minutes. And then we'll get a good start on 17. 17's easy. After this, 17 is totally easy. You'll love it. Okay. It is kind of cold in here. CuCl2, 0.6, 0.3, 0.1. Did you do those makeup problems?
I gave it to you last week.
That's right, you did. Okay. Here, I should pause that thing.